Okay, you can start.
Okay, perfect. Hello, guys. So today's paper is a unified framework for continual learning and unlearning, uh, with like people from bunch of institutions, RESP AI Lab, APFL, and University of South Florida, and also an institute in India. So that's, as I said, that's a paper of like continual learning and unlearning. So previously, in the previous like paper I presented, it was an unlearning paper. But in a real world scenario, you need to somehow continually unlearn, right? So combining continual learning and unlearning would give you a better, like realistic, like task design, I would say. So techniques used previously in continual learning and unlearning. In continual learning, Fisher information matrix is used in elastic weight consolidation. So you understand which parameters are important for which task. So you somehow need to retain the important parameters. For example, there are replay-based methods. So you have kind of a memory. There are regularization-based methods. So you add a term to the loss objective or loss function. So you're penalizing the network if it forgets the data it shouldn't forget, right? And there are, of course, knowledge distillation. In unlearning, as I presented before, Fisher information matrix is widely used. NTK theory, we talked about it with Brooke yesterday, neural tangent kernel theory.
I was talking about this, do you remember? I said if I
Yeah,
should maybe do some paper about
yeah,
this,
true.
if you
True,
guys
true,
knew
yeah.
NTK theory.
You know what? I think you talked about it when we were in Paris Seclay as well. I think we were like walking in the corridor or something like that. You talked about it too. So
Yes.
yeah, so basically, you just when you make the network wider, it approximates to a kernel function. So it gives you a linear kind of behavior. So you kind of know the network. It's kind of deterministic if you make the network in a like infinitely wide enough, or sorry, it's wide enough that is approximating to the infinity. It's becoming like a linear operation. So you kind of know the network. If you know the network, you can understand like which parameters are important for unlearning, right? So NTK theory is also used in unlearning. If you have the data, if you have the forget set, you can just do gradient descent. So you wouldn't decrease the gradients, but increase the gradients on the forget set. So you would somehow unlearn, or you would add some noise to maximize the error, like many methods, but knowledge distillation as well. So if you look at the both techniques, it is not written in the paper, but that's what I think. Both methods has knowledge distillation, right? So they use knowledge distillation in this paper, but uh, just to like imagine how they came up with this idea, I just wanted to list the techniques previously used in continual learning and unlearning, so we can see the intersection, which is knowledge distillation, right? So, okay, the novelty of the paper, the first paper to integrate them in a single system, like continual learning and machine learning. No one else has integrated them before. So this paper that was published in December 2024, so a couple of months ago, is the first paper that combines continual learning and machine unlearning in a single system. So, okay, they use a knowledge distillation. So they have like two teachers, one for continual learning and one for unlearning, and they have one single teacher. So they are trying to like integrate them in the like teacher, sorry, a student, right? Two teachers, one for continual learning, one for unlearning, and one student. And that's not really a usual knowledge distillation, because it's not only like transferring the knowledge of the teacher to the student, because teacher is updated after student. I will show you later. So it's not a usual knowledge distillation, but kind of a knowledge distillation. So yeah. So yeah, they show this figure. Okay, we have continual learning. The tasks are like flowing, right? Task one, task two, task n, stream of new tasks. And we have machine unlearning. Somehow you have like, again, the flowing tasks. stream of tasks, T1, T2, Tn, and you somehow want to forget some of the tasks. It can be a class, it can be a sample, and it can be a task itself, like classification regression. It can be anything. In this scenario, it's a class-wise forgetting, which can be one of the critiques I can make, because class-wise forgetting, I told it in the previous presentation as well, is not really realistic. Because let's say you have clients, right? So you don't forget the whole one age class, for example. You forget a client. At least in Nokia, we are planning to do something like that. So we are designing the task that Nokia can use it. So if you forget the class itself, it's not really realistic. So the company cannot use it, for example. But in this framework, this is class-wise forgetting. So yeah, you have continual learning, you have machine
I have a
learning.
question.
Yeah, sure.
So you have class-wise and sample-wise for
Mhm.
unlearning, right? And I think as you just said, we also talked about this last time. We had an unlearning paper that in many papers they focus on class-wise unlearning, right?
Yeah.
But how difficult is it to like? Is there a when you have a technique for class-wise unlearning, is there always some way to construct this into a sample-based unlearning method, or are these like fully distinct in some cases?
Not fully distinct, I would say, but they're pretty distinct. So I haven't seen a paper in unlearning that is working in class-wise, but it doesn't work. Sorry, it also works in sample-wise. I think there are papers like, but rarely. So most of the papers are just concentrating on either class-wise forgetting or sample-wise forgetting.
But what, like, in your opinion, do you think that so? What is the claim like that you need both because in some applications you will need class-wise, or is the idea more okay? We do class-wise because it can be easier to
Mhm.
develop ideas for how to better do sample-wise. Do you know what I mean?
Yeah, I think that's a good point. And I think, yeah, because for now we are somehow trying to modify the class-wise forgetting technique, which was using Fisher information, if you remember, to a sample-wise forgetting. So it helps us somehow. So I think definitely it would help. Like if some papers in class-wise forgetting, it would help the researchers in that are trying to do sample-wise forgetting. But
Hmm.
I believe sample-wise forgetting is way more realistic, and I don't. Yeah, that's a good point. Like integrating them both would be a nice option. Like um, okay, you have sample-wise forgetting, but you want to extend it to class-wise forgetting. I think if you combine them in a single paper, it would be a nice.
But isn't just to make sure I'm getting this, isn't sample-wise for getting strictly more general because you can always basically add a model that classifies a sample into a like if you have a model that's doing sample-wise unlearning, can't you
Mhm.
also turn that into a class-wise unlearning by just having a model that maps a sample onto a class? Or am I stupid? Wait, does that make sense?
Mm, I'm not sure honestly, but but
No, I don't think that makes sense. Yeah, yeah, I think it's
yeah,
not more general. Yeah.
okay.
I think it's actually really a distinct thing, right?
Not
Okay, well,
not completely, because Fisher information is used in both, of
yeah,
course.
yeah, but I mean, it's you cannot go from one. It's not trivial to go from one task to the other, right?
Yeah, definitely. Because let's say you're forgetting some samples, but you're forgetting in different classes, right? And you somehow need to maintain the accuracy of let's say class A, but you forgot a sample from class A, but you need to maintain the other. You're forgetting a subset of class A, but you need to
Yes.
maintain the accuracy in the other subset and in class A, right? It's a very challenging task. Like sample
Yeah,
wise
I think
is way
I
more
was
like hard, I would say.
I was thinking that maybe like you could just basically if there was a way to take every sample from one class and just forget every sample from
Mhm.
a certain class, but obviously that doesn't work because
Mm.
yeah.
Mm.
Okay, whatever. You can move
Okay.
on.
Yeah,
Thank
okay.
you for the response.
First, so in their framework, I mean, not really, but yeah, ideally, they have random order of continual learning and unlearning requests. And there's a single teacher that kind of integrates both. Okay. So you have many requests, continual learning, or learn task one, learn task two, learn task three, unlearn task two, learn task five, unlearn task four. So it's like learning and unlearning together. How do you do that? Like this. So you have a continual learning teacher, you have an unlearning teacher, and you have a single student. Okay. You have a bunch of continual learning requests and you have a bunch of unlearning requests. For example, forget the class, blah, blah, forget the class. Sorry, learn the new task, learn the new class. Actually, these are now not tasks. That's another kind of error in the paper because task, class, sample, they are different. So that if you call it task, it can be a regression classification also, right? Because that's another, like at least in unlearning papers, you can also forget the task, or in continual learning paper you can learn a new task, not only class, right? And in this, these are two distinct things, but they just use task to say the class, because in this paper these are continual is continual class wise learning and continual class wise unlearning, right?
So when they, sorry, just to see if I understand this. So if they basically, if they're adding a new task, what they
Mhm.
actually mean is just that they're adding a new class.
Exactly, but
Okay, okay.
that shouldn't be the case because uh, task and class and sample, these are distinct things. So in
Yeah, I
learning
agree.
papers or continual learning papers, you will see like, is this method is working for task or class or sample? You have the ticks. And if you use task here, what I understand is like changing the task, but actually this is just class. So maybe I'm not 100% uh, like correct, but that's what I think, that they shouldn't have used the new task samples here. Okay, whatever. So, okay, you have continual learning teacher, you have unlearning teacher, and you have the student. So whenever new task comes, you distill the information to the student. Whenever new unlearning task comes, you're just trying to minimize the chiasm divergence between the unlearning teacher and the student. So whenever new task comes, you just use the continual learning teacher and you use the continual learning loss, okay? And the continual learning loss has actually four different like elements, which is kind of a lot. So I will tell them all to you. So yeah, okay. So and you also have a buffer. You also have a memory, which is not maybe ideal because machine unlearning is a data private task, and if you have access to the data, I mean that's not really the ideal case. But probably they couldn't do it without the buffer, so they have the buffer, and it would be really challenging to do actually without a buffer. So yeah, I can understand that. I'm working on the same problem, so I can definitely understand that. Okay, new task comes or new class comes to forget, let's say. You're also forgetting it from the buffer. You're deleting it from the buffer, and you're not only minimizing the chiasm divergence between the unlearning teacher and the student, but also continual learning teacher and the student. So this figure is kind of deficient. Maybe they should have given another arrow there because, as I said, when a unlearning task comes, not only the chiasm divergence between the unlearning teacher and the student is updated, also a continual learning teacher is involved to maintain the other task accuracies. Okay. As I said, for unlearning, there's only one loss, which is chiasm divergence. But for um, continual learning, there are like four element loss, which is called continual learning loss. And those elements are cross entropy for training the student, basically just cross entropy, supervised learning. You have online distillation, just to distill the knowledge of the continual learning teacher to the student. Basic, not basic, but usual loss used in continual learning. You have contrastive distillation loss. This is basically to make the embedding of the continual learning teacher and the student embedding close to each other. This is just for that. And another loss, which is supervised contrastive distillation loss, and it's just for the student itself to make the intra-class similarities in the student close to each other. So making the positive samples close to each other and the negative samples, or like not negative, but the other class, like making the same class samples close to each other and different class samples further to each other, distant to each other. I mean, I don't know how they came up with like 4 elements, but in the end, the combination, the just summation of all these 4 is continual learning loss. And they also have like alpha parameters. Let me quickly show that. Yeah, cross entropy, online distillation, contrasted distillation, and supervised contrasted distillation. This is the final continual learning loss. Okay, and I will come like explain all of them one by one. Is it clear so far until here? I can explain again.
I think for me it's pretty
Yeah,
clear.
for me it's also clear.
Okay, so as I said, 2 teachers, 1 student. This is also called bad teacher. This is also called like good teacher. Okay, and 2 losses.
Wait, but
Sorry, Biruk,
yeah,
I
but
couldn't.
yeah, I still didn't see the use of the buffer in the
Yeah.
training.
So the buffer is just storing the new tasks or new classes, right?
Mm.
And buffer, like, it's just used in the continual learning teachers like training.
Mm.
So you need to somehow retain the information of the other classes,
Mm.
and to do that you need a memory. As I said here, maybe I'll show you quickly.
Okay.
For continual learning, there are like replay based methods.
Yeah.
So basically, this is a replay based method. There's a memory for the continual learning task. So you have a
Mm.
buffer, and while let's say you want to forget the task number 2, so you just delete it from this buffer also.
Mhm.
And yeah, okay. 2
Yeah.
losses: continual learning loss, child divergence loss, and 1 student. And continual learning loss is just 4 element. Okay, consisting of 4 elements. Okay, so there are 3 main components: feature extractor f theta, a classifier f phi, I think, and a projector for embedding features f psi or psi. And the buffer is like represented with b, so it just stores the data and the labels. Okay, and the size is b braces. Okay, so yeah, 3 main components. Okay, because we will use it all the time: f theta, just a feature extractor; classifier f phi, right? And f psi for embedding features. So embedding, just basically a projector for embedding. Okay, so the first loss is the cross entropy loss. So basically, the classifier, right? And the classifier and the feature extractor, basically the model for the student, okay? So I really don't understand why they made them discrete, because I don't see any point. They could have just say like, for example, they don't need this. We can just say a model, and we can just say f theta, for example. But whatever, they use this. So combine the output of the feature extractor and the classifier, they say, which is basically the model itself, right? And this is the current task data set. And you're combining it with the buffer. So the data set you already have before, right? Buffer plus the new task samples, okay? So the combination of them. And then you use it and you just then train the student with this loss. Okay. So the first loss is basically cross entropy. You have the data set plus the buffer. So new data set plus the buffer, and then you're just training it with cross entropy. So basic so far. So things are getting complicated. So online distillation loss. That's basically a usual loss for knowledge distillation. So just concentrate on this part. Okay. You have the weight. Just the weight I will tell you later. So you're kind of minimizing this, right? Minimizing the distance between the teacher model, and the student model. Okay, so you're transferring the information in the teacher to the student for the continual learning task. These are all for continual learning. As I said, like continual learning loss. Okay, the first one is cross entropy. The second one is online distillation loss, to transfer the information in the teacher to the student. And there is also a weight. So weight is basically the like confident samples. So for the confident samples, like okay, like just dynamically scales the importance of each sample based on the teacher model's confidence. So what you see here, when this one is more, so when the output of the teacher model is more, this is more as well. Okay. So yeah, that there's a weight, not really important, I would say, but yeah, there's this loss. So you want to minimize because this is a loss, and actually there should be a minus here. I think they for not here. Sorry. Okay, it's okay. No problem. I'm not sure actually, but we need to minimize this one. So maybe there must be a minus here. Not sure, but okay. So online distillation loss to transfer the information in the teacher to the student. Okay. Then contrastive distillation for embedding alignment. Okay, just focus on the fifth equation. I will explain the sixth one later. So contrastive distillation loss. So H is just a function that represents the similarity between the teacher and the student. If you look at the sixth equation, that's just the dot product of the elements like I and J. So basically the dot product plus the temperature parameters. Okay, so looking at the just this is the positive samples, because this one denotes the set of teacher embeddings with the same label as the student. So the teacher embeddings that has the same label as the student, so positive samples on the nominator, and negative samples on the denominator. So the classes from the teacher that doesn't share the same classes as the student. Okay, so there has to be a minus here because we want to make it bigger, right? We want to make it bigger. If this is big, we are on the right track, right? Because we want to make the similarity, the H function represents the similarity between the student and the teacher bigger. If we make it bigger, the loss is bigger. It shouldn't be the case. So there must be a minus here, a critical issue in the paper. That's a really critical issue in the paper, I
Yeah,
think.
yeah, I
Yeah,
think the main contrastive formula, the contrastive loss. So I think there is a minus in the contrastive loss.
definitely.
Uh,
Maybe
So you,
also in the
you're
previous one.
saying are you saying they just have a typo, or do you think it's implemented wrong?
I think there's a typo because if they implemented it wrong, I think it wouldn't work
It
because
won't work, yeah.
yeah, maybe it's a typo, yeah. But there's a minus in the contrastive loss, or just a similarity divided by the sum, and then they just log the probability. We have the exponent for the softmax, and then I think there's a negative sign
yeah,
in front of the.
yeah, probably because these are the positive samples, right? So we want to make the embedding of the student and the teacher when they have the same labels closer to each other, and when they have the like how do you say different labels, we want to maximize the distance. So when it is big, we are on the right track. So the loss shouldn't be big. So there must be a minus.
Yeah.
Yeah. Okay.
So the H is big when?
The student embeddings and the teacher embeddings, when they have the same labels, right?
Yeah.
Should be close to each other.
Then it's big.
Yeah. So the H is representing, as I said, just the similarity because it's basically the dot product, right? So
Yeah, I see, I see.
yeah.
Okay. So it's the angle basically between the embeddings exponentiated with the temperature is the H.
Yeah, just
So basically, if they differ, you want the loss to be small, right?
yeah. So you want
So
to loss small, but when the embeddings are matching, when they are close to each other, but the positive samples in this scenario, in this equation, it means getting lower.
yeah, oh yeah. So basically, when they're the same, then the loss is large in this case.
Yeah. Yep. So okay, let's continue with the last element of the loss. Look, there is a minus here, and that's basically the same function, right? The same function, but there's a minus and expectation here. So I think they forgot the minus here, or also the expectation.
Yeah, I think it's just people don't really care because it's not like you're implementing this formula. You're gonna build it from some torch modules, right? So
yeah,
you don't really
yeah,
care.
yeah. Probably they.
But I agree that it's wrong. I think you're right.
Yeah. So this loss, as I said in the beginning, if you remember, guys, for the intra-class similarity. So we want for the student, by the way, not for the teacher. Not teacher is not involved here. For student, we want the same class samples close to each other, and the inter-classes, like this denominator, so the negative samples, kind of, like distant to each other. Okay. So when like that's an additional term. I don't know if it was needed. I'm not sure, but yeah. To sum up, they have like 4 elements, cross entropy for the student training, right? Basically the student model, theta and the phi. And online distillation loss to transfer the information in the teacher to the student, right? With a weight. So when the model is more confident, you can transfer it more, kind of, right? Yeah. Online distillation for the knowledge retention or transferring the teacher knowledge to the student. And the contrastive distillation to align the embeddings of the teacher and the student. And another supervised contrastive distillation loss to make the same class samples in the student close to each other. 4 elements, and then we add them together. So we have alpha 1, alpha 2, and alpha 3. So probably for cross entropy, since it's really like primitive or really like important, they don't have a parameter because student must learn with the new flowing data, right? So they don't have any parameter here. But for the rest, there are like parameters. And by the way, this buffer is not infinitely large. They use different buffer sizes, and it's affecting everything. I will show you later. And if it was infinitely large, I mean, it wouldn't be really memory efficient. Still, it is not really memory efficient, I would say, because in unlearning, we don't even use a single sample. Like we don't store a single sample because it's a data private subject, right? But at least they don't have the infinitely large buffer. Okay, so cross entropy, online distillation loss, contrastive distillation loss for aligning the embeddings, and supervised contrastive distillation for class similarity. Why supervised? Because we know which samples are belonging to the same class, so we know everything. We have the labels and so on. That's why it's supervised contrastive distillation loss. As I said, the final continual learning loss is this. So what do we have left? unlearning loss. But before that, there's a momentum update. I don't know how they come up with this, but yeah, for the feature extractor, for the classifier, and for the embedding projector, they update the teacher using this momentum updates. So there's a momentum coefficient, which is m, and there's an x, a random variable from the Bernoulli distribution. So yeah, I don't know how, but somehow they come up with this to update the teacher weights. So how do we update the student weights? With cross entropy, right?
Wait, can you go back to the momentum update?
Yeah, sure.
So there basically you have m.
Uh-huh.
So if m is 1, you have, okay, I see. So if m is 0, you have no momentum. You just
Mhm.
basically update with
You
either
just
the
do the
teacher
same.
or the student. Yeah.
Yeah, if m is 1, you just don't use the momentum update, right?
Yeah, then you just either take the student or the teacher as your, right?
If there's no momentum update, yeah, it's a good question. What do we do? Just
So
take
so if m is 0, then you just have 1
the.
minus x theta t x theta s. So basically you have a Bernoulli chance if you get theta t or theta s, right?
Mm-hmm. Yeah,
And
exactly.
then if you add momentum, then you just have basically a regularized
Yeah.
version of that, which basically, yeah, but what is the point of that? Because aren't you just, oh no, okay, I see. So if you, okay, I understand. So if you
Mm-hmm.
have no momentum, then it's
Mm-hmm.
fully probabilistic. You just basically take a chance, and then you either fully put it onto the student theta or the teacher theta, right?
Mm-hmm. Yeah, exactly. And
And then if you have a momentum, then you basically add a deterministic component.
mm-hmm. I mean, I don't know. So I think, let's say we have the momentum. So let's make it like 0 for now. So
Mhm.
we have this term, right? So that's kind of another way of making the student and teacher close to each other, I think. Because if you didn't have the momentum, if the m is 1, you just don't have this component and teacher are not just updated like externally. So it would be the just the uh,
Yeah.
for loss combination. But now you have an extra step to make the teacher and student close to each other. I don't know how they came up with this, but somehow they did. I don't know if it is used in knowledge distillation papers. I don't know much. So I don't know. They just have this. Okay.
I mean, we know knowledge distillation, I think,
Huh?
somewhat. I think we know knowledge distillation somewhat because we did like a bunch of papers on it, right?
Yeah. True, but
So I've never seen this kind of thing. But I mean, it's a kind of momentum update, so it does make intuitively, but they don't say, oh, we have this from this paper or
no,
something.
just they
They
have the
just
stuff.
cooked it up themselves.
Yeah. By the way, for the buffer sampling, because they don't use the whole buffer. They sample some data from buffer. They used an algorithm from 1985. I don't remember the name of the algorithm, but that algorithm is from 1985, for example. When you said if they like used the momentum update from a paper, no, they don't say explicitly, but for the buffer sampling, they have an efficient algorithm that was invented in 1985. Okay. So unlearning loss was left, right? So unlearning loss, I think I told you already in the main architecture, this is just child divergence, nothing else for unlearning, okay? Uh, so yeah, 4 elements for continual learning loss and final continual learning loss. They also used another like intermediary step for momentum update. They update the teacher parameters, like all of the teacher kind of parts, like the feature extractor, classifier, and the projector with they updated with a momentum, and we have the unlearning loss, just basically child divergence. So B is the bad teacher, right? So WU is either 1 or 0. So when you're updating the child divergence here, right? If WU is 1, you're just updating the like just looking at the child divergence between the student and the UL teacher. If WU is 0, you're just looking at the child divergence between the teacher and the student, because okay, you're unlearning, but somehow you need to retain the knowledge. To retain the knowledge, you're not only looking at the child divergence between the student and the teacher, also the CL teacher, so the good teacher that has the previous information, and the student. And while doing that, you're deleting the data from this from this order. So you're like, okay, I got the order that I should delete the class 2, for example, and I'm deleting the data from class 2 in my buffer, then looking at the child divergence between the student and the teacher. This is really complicated, right? I don't know how they came up with this, but basically, probably what they did was, okay, they knew knowledge distillation, and they wanted to say, okay, we need to do something in continual learning and unlearning. So continual unlearning, let's say we have two teachers, they said, and how we can, like, how can we create the losses? Okay, they use the child divergence here, they use a bunch of stuff in this part, but actually that's not only this like in between student and the unlearning teacher, it's also this child divergence is also in between continual learning teacher and the student. That's that's a deficient like graph or figure, but yeah, is it clear for you guys? I mean, that's complicated, but somehow, yeah, they came up with this. So maybe you want to look at this. As I said, if the
I think it
W
makes sense.
is 1, they don't look at the teacher and the student child divergence. They don't look at it. 0. If the WU is 1, then they're just looking at the bad teacher and the student. So bad teacher is the unlearning teacher, right? So they're trying to minimize the child divergence between the bad teacher and the student, but they also look at it for the like for the teacher and the student, for the good teacher and the student. So you're not like, okay, the student is our king in this setting. Student is everything in this setting, okay? So we are not, let's say we have a model, we are not using the outputs of the teacher. No, our student is responsible for everything, okay? So, okay, the bad teacher is making it unlearn with this component, but we need to somehow retain the knowledge that is coming from the teacher, like the good teacher. So we have two components here, and there's the basic child divergence formula. So unified loss is, again, like just like in continual learning loss, they have two elements, the continual learning loss and the continual unlearning loss. So 1 minus gamma, and the gamma is a context sensitive weighting factor. So it is kind of a hyperparameter to optimize, okay? Sorry, not a hyperparameter, sorry, it's either 1 or 0, I think. So if the task is continual learning, it's just focusing on the continual learning task. If the task is continual unlearning, it's only focusing on the continual unlearning loss, because continual unlearning loss is already has the, you know, teacher information. So okay, this is not a hyperparameter, I said it wrongly, but okay, we have gamma here also. And another ChatGPT how do you say moment where gamma is context sensitive, blah blah blah, allowing seamless transitions. If you use ChatGPT enough, you would say that this is a ChatGPT word, definitely. And I don't know, like, why did they use it even here?
Wow, the allegations.
What?
Seamless.
Yeah, allowing seamless transitions. Why?
What do they mean? What do they mean by seamless?
Probably
Good.
they, I mean, that's just a ChatGPT additional word. I mean, You wouldn't write it right after the formula, right?
Yeah, it sounds a little bit
Suspicious.
unspecific.
Yeah.
Base and
So
test.
interestingly, another critical point, or another point that I can criticize, I would say, the algorithm is in the appendix. Why? That's the main point of your paper, right? So why is it in the appendix?
You know why?
Why?
Do you remember when we were told to not put math on the presentation?
Yeah.
Now it's even like don't put math in your paper. People are gonna be
Yeah.
scared. You just have to
Yeah.
put it in the appendix.
I don't understand this. Yeah, I definitely don't understand this. Okay.
Yeah, I mean, I guess it's you don't really if you understand all the sub steps, you don't really necessarily need the full algorithm in one box, I guess.
Mm,
But I agree that this should be probably in the main text.
yeah, I also think that way. Okay, so this is pretty complicated from here because it's also deficient because you can have unlearning task, you can have continual learning task. It changes. So I created a example to better understand the steps. Okay, let's say we have three learning and one unlearning task. So we want to learn T1, learn T2, unlearn T1, learn T3. How do we do that? As we know, we always have three parameters: theta. Okay, I changed the order, but it was on the third order before. So okay, theta, psi, and phi, right? And continual learning teacher is the same. Unlearning or bad teacher, same, and we have the replay buffer B. And this is initially empty, of course. Task 1, learning T1. We initialize the student and the continual learning teacher with the identical random parameters, okay? And we are setting the gamma to the 1, if you remember, guys. So this is 1 or 0, as I said. So we are only focusing on the continual learning loss for now, because we are it's a continual learning task. Learn task 1, okay? So gamma is 1, and buffer B is empty for now. We are loading the T1 dataset, for example, classes 0 and 1, or class 0 only. They made a bunch of experiments, but only class-wise. So for each batch of data, you calculate the classification loss or the cross entropy to update the parameters of the student. So the buffer is empty, so only cross entropy in the first step is contributing to the loss. That's why I said this is not entirely enough, because like there are many if and else's which they don't show here. Another critic actually, like, okay, I understand that their algorithm is really complicated, but they could have just given like continual learning algorithm and continual unlearning algorithm. So they would say, okay, CL algorithm here, sorry, UL algorithm here will be explained in the algorithm 2 section. So they would say, okay, UL is here, but it's on the right hand side, for example. Okay, they didn't do that. So okay, let's go back. So as I said, since the buffer is empty, only the cross entropy is used. Okay, then usual gradient descent to update the student parameters. So they update the buffer, taking the T1 samples. Okay, now I remember the name because I see it. Reservoir sampling. This is a method that was invented in 1984.
Oh, reservoir sampling. I mean,
Yep.
I
Yep.
think I know, definitely know reservoir sampling.
Yeah, so it is an efficient, data efficient way of sampling. Okay, that's a fast way of sampling, an efficient way of sampling. Okay, not really important for this, but they just tell that we use this. Okay. Okay,
I'm trying to remember where I learned this. I don't remember.
probably another paper because you need to sample somehow.
No, I remember I learned this in a class, but I'm not
Ah,
sure where. I
okay.
had a class where we did derive this algorithm. Okay,
Mhm.
whatever.
So as I said, buffer B is not infinite, and its maximum in this paper is 5,000. So if you're using CFAR10, for example, each class is like 6,000. And if you're like the T1 dataset or task 1 is consisting of 2 classes, it will be 12,000. So you don't put all the data to the buffer B, you put some of them, and from reservoir sampling, as I said. Okay, then you learn to teach a student, then you learn that you update the teacher parameters using the momentum update. What do we see here? This is not the usual knowledge distillation. In the very beginning, I told you guys, this is not a usual knowledge distillation. Why? Because student, at least in the first step, in the first task, student is updated before the teacher. So kind of teacher is learning from the student in this setting, right? Because the student is updated before, student is learning with cross entropy, then the teacher is getting updated with the momentum update. Maybe that's why they used momentum update here. Maybe. Okay, so we learned the task T1. Let's learn task 2. So maintaining the teacher from the previous step. So again, the gamma is 1 because we are learning. We're not unlearning. We are using the continual learning loss. We load the T2 data set. And for each batch of data, we first calculate the cross entropy, like here, the same. The student learns. And then we sample the data from buffer B. Then we have the different loss, right? Loss elements, because continual learning loss was consisting of online distillation, contrastive distillation, and supervised contrastive distillation loss, right? So before we didn't have the teacher because we don't know in the first step. So we cannot really align the teacher and the student in the first step because teacher is just random, right? But in the second step and after the second step, we use the other elements. Online distillation, contrastive distillation, and supervised contrastive distillation, which was for intra-class similarity, and the contrastive distillation is just the teacher and student embedding alignment, and online distillation is just a distillation, actually, to distill from teacher to the student. Okay, then we aggregate the losses, and then we update the student parameters. Then, again, the teacher update and the buffer update. So if the buffer is full, again, using the reservoir sampling to maintain the diverse representation. So reservoir sampling in this setting is really important. It is efficient. It is giving you enough diversity. So in buffer, you don't only have like from T1 to from T2 because it's a continual learning task. You need to maintain your accuracy in the previously learned tasks. So you need to somehow have data like equally from, not equally, because you're being more tendent to forget the first task you learned by while going further and further, right? So maybe, I'm not 100% sure, but maybe you would need a little more data from the first task to not forget it. I'm not sure, but reservoir sampling is efficient in this setting. Everything clear, guys? Let's unlearn if everything is clear.
I think for me it's clear.
Okay. So let's go for the unlearning. So we initialize the unlearning teacher because it is not initialized yet. So we don't have the T1 knowledge because we need to unlearn the T1, right? And we are setting the gamma to 0 because now we will use the this part. The gamma should be 0. We shouldn't use the contrastive learning loss. We should use the continual unlearning loss, which is this. So just basically Kyle divergence. Okay. Okay, we are unlearning T1. So unlearning process is we're identifying the T1 samples. So for each batch, okay, WU is 1 for T1 samples and 0 for T2 samples, because we will retain the T2 and we will unlearn or forget the T1. What was WU? This one, right? So we will, for class 1, because we will unlearn it, we will use this. For class 2, we will use this to retain the knowledge. Everything is clear now, right? Because when I was first explaining this, it was even not clear for me because I forgot what was WU. But for the task to be forgotten, we use this because this is the bad teacher and the student. So we want to maximize the bad teacher and the student for one class, right? And for the other class, we want to use the teacher and the student. So the good teacher and the student, because okay, we want to forget, but we want to retain the knowledge for the other classes. Okay, so WU is 1 for T1 samples and 0 for T2 samples. Then we calculate the unlearning loss. Basically this, I already shown you. So this makes the student follow the bad teacher for T1 and original teacher for T2, or the good teacher for T2. Then we buffer, we update the buffer. So remove the T1 samples from buffer B and retain only T2 samples. Actually, this is before the second step, I think. Otherwise, we would make the, like if we, like we cannot do this because we have, no, actually we don't really use the training. So, okay, no problem. But yeah, we need to remove the T1 samples because we are unlearning, and I mean, this shouldn't keep the information here, right? This continual learning teacher shouldn't keep the information here. So we update the buffer. Okay, then we update the teacher again with the momentum. So now the teacher model has forgotten T1. Clear for you guys?
Yeah, I think so.
Clear for you, Brook?
Yeah, it is clear. Yeah.
Okay, perfect. So again,
Well,
just to show you, again, learning T3. As like just task 1 and task 2 was the same. So we have the task 4 here, which is learning the task 3 or learning T3, another subsample from the data set. We are using the updated teacher model. We already have the teacher with T2 knowledge, but no T1 knowledge. Supposedly, probably there's still T1, but not much. So gamma is again 1 because this is a learning task. This is not an unlearning task. Okay, so we use the cross entropy loss for the student. We sample from the buffer using the reservoir sampling. It was previously only T2 samples, right? So we calculate the distillation loss, we aggregate the loss, we update the student parameters again. Okay. Then we update the buffer for the later use because we will sample just like from here, like in here. Because here in this loss, we are using the T3. And then we are sampling from buffer B, which doesn't have the T3 yet, right? Which doesn't have the T3 yet. So we are retaining the knowledge in these steps. We are learning the new task here, and we are retaining the knowledge in these steps. Okay. We aggregate the loss, we update the student parameters. Then after we learned the T3, we are updating the teacher. So actually, as I said, it's like not a usual knowledge distillation. We are kind of like teaching the teacher from the student with this update, right? Okay, that's it. That's basically it. 2 losses, 2 teachers. 1 loss has 4 elements, and only a single student. There is the king. There is the main character, right? So we have the results. They only use CFAR10 and CFAIR10, which is basically the same as CFAR10. I have never heard of it, by the way. I don't know you guys, but even Google, when you Google it, it's just saying, did you mean CFAR10? Like, just let me show you quickly.
this one is sci-fi thing,
See
right?
fair,
And
I
it
say
seems
CFAIR10.
like Facebook.
it seems from the Facebook research.
So yeah, probably a duplicate free variant of CFAR10 test set. But it's even asking me, is it like, did you mean CFAR10? So yeah, it's not
Is it
easy
is
to
it
find.
is it see fair in the sense of like fair because there are no duplicates? Like it is fair It doesn't mean fair is in meta, right?
Like Facebook AI research. Maybe it is not.
Yeah, I
I'm
think
not
it's
sure.
which one is it?
Let's see the paper. Actually, no,
Oh, I know
just
this
the,
group.
just the yeah vision group in Germany.
Jena, yeah, I've heard of this group.
Okay, so
Interesting.
yeah, just a variant of CFR 10. To be honest, guys, I have never heard of it, and I have never seen it in unlearning papers, at least in unlearning, never. Okay, CFR 10 is okay, but CFR 10, never even heard of it. If they used CFR 100, it would be crazy. It would be really nice, but they didn't.
I guess it's just CFR10 just with no duplicates, which
Yeah,
I mean it makes sense, but it's still a very easy data set.
yeah, definitely. But I mean, and these are like 32 by 32. So why didn't they use like Stanford cars or like birds, Carnegie Mellon birds kind of data sets, which is another like point. The conferences would criticize a lot, so that's why I believe, even though this paper is kind of novel, okay, it's a good paper, I don't think it would get accepted from the top conferences without modifications. But with modifications, definitely, and it's a great starting point for
Do
continual
they
learning.
only have CFR10?
Huh?
Do they only have CFR10? They only use CFR10,
And
basically?
CFAR 10, yeah, two data sets.
Yeah, I mean it's the same data set, like
Yeah. They only
pretty
use
much.
CFAR 10. And another point
Okay,
that you they don't have the
yeah.
baseline because they are saying, okay, we are the first paper, so we don't have the baseline.
For continual learning,
I mean, yeah, no,
Mm.
or
for the
continual unlearning, or what?
for the continual learning, they say they don't have the baseline. They only compared with the retrained versions. So let's say you have class 0, 1, 2, 2, 3, 4, 5, 5, blah blah blah. So you unlearned this and this. So they're comparing their method with a model that was trained only this, and the others. Not this.
Mm,
So they're comparing it with
okay.
only that. Another
Mm.
critical point because, I mean, okay, maybe not. You don't have the continual learning, but you could have used like your method and let's say an unlearning method, like without
Yeah, I
using
understand.
continual learning. Yeah, I mean, you could have
But
somehow modified it to use it as a baseline.
but how good is the performance? I mean, you're the expert, right? Like,
Yeah.
if you
So
don't have a baseline, then you kind of have to judge it based on vibes.
yeah. So I would say since they used a huge buffer size in this setting, and as you can see, it's pretty good. So they unlearned task 2 only, because look,
Mm.
learn T1, T2, T3, sorry, unlearn T2, learn T3, learn T4, learn T5. So up to this point, it's the same as I gave you as an example, right?
Mm,
Yeah.
Then they learned T4 and T5 extra. So in buffer size 500, like, sorry, 5120, it works pretty well. It retains the previous knowledge, but for a small buffer size, especially for the like first tasks, they are terrible, like 24% only in the uh,
yeah.
even the like afterwards. Like, I mean, if you don't have the memory, this method usually doesn't work. So I think uh, for this one, it works really well, but we're trying to, in machine learning, we're trying to not store the data. Maybe I'm
Yeah.
not. Maybe I'm somebody that is hard to convince, but yeah, that's a
I
great.
don't know. It's just I feel like if they want to publish that somewhere, they're just gonna ask to try another data set because
Mm,
CIFAR 10 it's sort of similar to MNIST in that way. There are many situations where you have a model that will work, but it will only work specifically for MNIST or CIFAR 10 because it's
many,
such a simplified situation
yeah,
that it
many things.
really doesn't
Even micro.
generalize well. And if it's
Oh,
already kind of not struggling, but you need a lot of memory
yeah,
to make CFR10 work, that's I don't
yeah.
know.
So actually, you know what? In my like research, I found the method. It can be even published in NeurIPS kind of crazy conferences, I believe, because I just changed the Fisher information matrix. I said, okay, the second order gradients are approximated as
I'm
just
gonna cut this out,
square.
don't worry. You can say
And
it.
huh?
You can just say what you're saying. I'm gonna cut this out of the recording though,
Okay, okay.
so people don't steal your shit.
Yeah, yeah, don't worry, it's okay because it doesn't work. It only works in
Yeah.
MNIST. That's why I'm telling it. So
Oh, okay.
yeah, don't worry. You can use it, guys. If someone is seeing this, you can try. It won't work. So I was like, okay, second order gradients, like in Hessian matrix or Fisher information matrix, are approximated by taking the squares of the gradients, not the second orders, but the first order, the squared. They approximate it.
Yeah.
But since it's the first order derivative, why are you taking the square and losing the direction information? Because when you take the square, it's always positive, and while perturbing the weights, you need to like calculate it in two different directions, plus and minus, and it makes
Mhm.
the process really longer than it can be. So I was like, okay, just take the first order derivative and perturb the weights in one direction, which is the positive. You don't need to calculate it for positive and negative, right? Because you already know, you already have the direction information. You didn't lose it by taking the square. I was like, wow, let me try. And it worked amazingly well for MNIST. I was like, damn, I found the net. And I just
Gold mine.
checked on Scholar everywhere, like with ChatGPT, with Perplexity AI. It was not used before. Then I tried it with CFAR 10. Even it's really basic as well, but of course way more complicated than MNIST.
Yeah.
So it failed in CFAR 10 and it failed in all the other data sets. So yeah.
Yeah,
Yeah.
that's tough. But that's what I mean, right? Honestly, we should like ban papers that use, especially MNIST. I mean, CFAR 10, as you said, is a lot more difficult, but already like still CFAR 10 is it's such a really a toy problem. You
Yeah,
don't really learn that much by showing that you can do it. You can fit a potato onto CFAR 10
but
or
for novel like methods like this one, I think because there's no any like integration of continual learning and unlearning other than this paper. At least there wasn't. I don't know if there's any now. So I think they can use even MNIST for these kind of novel methods because it's a good starting point. Uh,
Mm.
because
yeah. I mean, I'm not
yeah,
against it in general,
yeah, yeah, yeah.
but do they say if they have tried bigger
No,
data sets?
I don't think so. No. So
But
they
why?
only used CFAR and CFAIR.
Why
So
not?
I don't know. Probably they didn't have enough GPUs, maybe. I don't know.
Yeah, sure, bro. Did you see who was publishing this? They definitely had the resources. I don't
Uh,
believe that they don't have it, but I don't know.
yeah,
There might be some good reason for why they
yeah,
didn't do it, but maybe we're just maybe there's some reason I don't see it right now, but
yeah.
I don't know. If I was a reviewer for this paper, I mean, I would have to read it a lot more in depth, but I would definitely say, could you try doing it on a bigger data set?
Yeah, true. So when you look at the results for a big buffer size, this is not batch size. I was like confused by this, but no, this is buffer size. It works really well.
Mm.
The buffer size is big enough, so it like has the, how do you say, knowledge for the previous tasks. And
Mm.
they tried like bunch of different stuff as well, like learning the first 5 tasks simultaneously, for example.
Mm.
Uh, so I think no, not simultaneously, but one by one, because otherwise the T1 wouldn't be this low, right? Yeah, yeah. I think because look, the last task is the highest, so I think they used continual learning here, like sequentially learning the tasks, not simultaneously. Okay, but they changed the tasks to the single class. So before it was like 2 classes. One task was learning the two classes like simultaneously. But now it's just one class. So they also tried it for the buffer size of 200. It works terribly because look, the class one accuracy is like just 15%. So you just don't retain it even for the class 8. When you increase the buffer size, it is working really well. It's like 78% for even the first class you learned. So yeah, it would be easy to forget, right? So yeah, for the large buffer size, it works really well. And for unlearning tasks, you unlearn T2, T4, and T5. So even in the large buffer size, it can unlearn, right? Not really different. So it's unlearning the T4, T5, and T2. For unlearning, there's no problem, but for continual learning, there's a problem for small batch sizes. When the buffers, sorry, buffer sizes. When the buffer size is 5,000, no problem for learning or unlearning. Works very well. But they say larger buffer size results in better retention. But they say this is making the unlearning, yeah, but worse at unlearning. Actually, no, I don't think so, because maybe in some other experiments they had a worse result for unlearning, but look, like this is even better than the previous ones in terms of unlearning, right? So large buffer size kind of solves all the problems. They talk about it
Yeah.
a little bit. They even have a mathematical approximation in the appendix.
Mhm.
So they say, okay, effect of buffer size. Larger buffer helps retain knowledge from earlier tasks, but it also makes it harder to completely remove information or completely forget. I can't
Mm.
understand. Maybe they had it for different tasks, but at least for the task design in CFAR 10, no. So, okay. For the critics of the paper, I think I already told you, but for example, this part, I just wanted to check it with AI detector, and it was like 100% likely AI. And it
But
from
is that
here,
accurate actually? Is it accurate?
it's not entirely accurate. It's not entirely accurate, but I would already tell it by looking at it. Like, we don't even need an AI detector because look, Aaron, like these baselines enable a rigorous evaluation of our framework's effectiveness in tackling tasks typically handled separately, establishing a comprehensive benchmark. So I think this comprehensive, like establishing,
Yeah, it sounds a
tackling,
little
rigorous,
bit
especially rigorous, just AI, Yeah,
sounds a little bit like they got some assistance.
yeah, that's okay.
Someone proofread the script, you know?
Yeah, yeah. That's okay. That's okay. Let's not criticize that much because it's a good paper and it's a good
Yeah, I
like
mean, who cares? Like,
yeah.
it's not like the results are different because
No, no,
of
no.
some tech.
That, that's just the
So,
idea is definitely not AI generated. I think that's a good idea. That's a
yeah, it
good
is.
outcome. But I would say like there's a critical mistake in the formulation. Equation 5, for example, there has to be a minus, I think. And why used CFAR 10? I was like confused because
Mm.
I mean instead of that you can use another data set like Stanford cars.
Yeah.
I think just as like probably it didn't work for Stanford cars, so they were like, okay, let's not use it.
Yeah, that's what I'm thinking, right? Probably, honestly, they like. There's no way they did all this effort and then only tried C for 10. Like they
Yeah,
definitely tried with something else.
yeah, probably, but maybe it was not working as well. Probably it would work if it was working CFAR with CFAR 10 that good. Probably it would work okay with Stanford cars,
Yeah,
but they were like, okay, it doesn't really like in 80s, in 70s, so maybe for the sake of our paper, we shouldn't include them. Maybe.
but I
So
mean, it's a new kind of problem, right? This
yeah,
continual
yeah,
unlearning stuff.
yeah.
So maybe it's just a difficult.
That's
It's
really
just
a difficult problem.
a
Yeah,
difficult task, and it's not really their fault, you know.
definitely a difficult task. Even unlearning itself is a difficult task.
Yeah, yeah, of course.
So, as I said, they don't have a baseline except for the retrain part. And it's not data private or memory light. So it's really memory heavy because of the buffer. And as
Mm.
I said, the, I mean, why did they like made them like distinct the feature extractor and the classifier because they don't use them separately. So the model and the embedding projector can be like distinct, but I don't understand. I don't see the point of making these two distinct and like showing the momentum update like 3 steps instead of 1 step. I don't know.
Mm.
So
Mm.
okay, that's all for this paper.
But what do you say? So just a point. We
Mhm.
talked about in the beginning about sample versus class based unlearning. To me, at least, correct me if I'm wrong, it seems that really in practice you would usually have sample based, but even continual, right? Like if I imagine you have a bank or something and you have a system, then you will have to continually add some clients, remove some clients. It's not like
Mhm.
you get all of the clients you want to remove in
Yeah.
one set and then you do one training. It's going to
Mhm.
be pretty much a continual setting, more or less, right?
Uh, for unlearning, you mean? For
Yeah,
sample?
like you don't get all of the, like the idea would be that you have some clients and they want to be removed from your model, but
Mhm.
they're not going to do it all at once. It's going to be like as it basically
Mm.
continually.
Yeah, so that's why I believe in real world scenarios, it's always continual unlearning, right?
Oh, okay, yeah, that's what I meant.
Yeah, yeah.
Mm.
In real world scenarios, it's always continual unlearning. It's never like, okay, client one wanted to be forgotten. Let's wait for the other clients. So okay, like the client two, client three, client four. But I mean, client one is still waiting to be forgotten, and you didn't forget it, right? Right?
Yeah, yeah, yeah. Like ideally, if you have some, I don't know, if you have some social media or some platform or something,
Mhm.
someone has an account and they delete the account, then you pretty much want to remove the information. Then you don't want to wait and then do a retraining
Yeah,
every 2 months or something like that, you
yeah,
know?
yeah. Definitely, you need to do it, like instantly. But
But you said
uh,
you said this is it's a new task. Does that mean there is no research at all, pretty much, on sample-based continual unlearning?
yeah, continual unlearning. Like I think for sample based, I don't think so. There is one, but
Anything that could exist?
I don't really think so. But this one
That's
is,
funny because it's like the most realistic setting, I feel like.
but really, really
Mm.
complicated. Even the class-wise continual
Yeah.
unlearning complicated, as you see in the paper. There are like many missing points. They didn't even use a big data set, like or a more challenging data set than CFAR 10. They didn't even use CFAR 100, for example.
Yeah,
So
yeah, that's
even in this class-wise continual unlearning, there are many challenges. So class-wise continual, like sorry, sample-wise continual unlearning, it would be really challenging.
Hmm. that's like that's not great. That's so
Yeah,
hard and so practically necessary at the
definitely.
same time.
Yeah. So we can maybe stop the share, like sorry, stop the
Yes, I'm
recording.
gonna
Then
record the
maybe we
recording.
can, yeah.
Thanks for
Yeah.
your talk.
Thanks for the presentation. Yeah, it was
Thank you.
really nice.